All right, my name's Pete Stenger. I'm from Northrop Grumman in Baltimore, Maryland. And over the last 5 years or so, we've been sponsoring a senior design project with Florida State University and FAMU. And we've had this X-band radar that investigates SAR image forming, and we've been advancing it each year as part of this senior undergraduate design project. And this year the idea was, well, what can we do with a software radio? Because there's a lot of commercial interest in there. You look at the data sheets, they can do a lot. The bandwidth is modest, but you can do some radar things. Covers a pretty wide frequency band. You can upconvert that to higher frequencies with one conversion and things like that. So it was very appealing from an idea standpoint. Let's try and see how we can get that to work as a back-end receiver exciter in a SAR radar that does digital beamforming. So myself and a mechanical engineer, I have an RF background, but there was 4 students, undergraduate students, in their senior project that worked this past semester. So here's an outline of my talk. I'm going to go over the goals we established for the team. The goals are based on the syllabus for the course. There was a professor, so we had to meet the guidelines of the course syllabus for this class. I got credit for it. Then I'm going to go over the system concept we pursued, give you a context on what we're trying to do, big picture, ConOps. There's a conversion to X-band component. The USRP, starts at the lower IF. You can't get the X-band. And to keep a reasonable antenna size, we had to upconvert. There's an electronics module which contains the USRP and other electronics to do the full thread radar function. And then I'll go into more USRP-centric topics, like how we generate the waveform and how we receive it. We're doing some MIMO and TDM, so we're switching between antenna elements and at the same time coordinating a waveform. So we have some timing coordination to do that's a challenge. Then I'll show you the measurement scene we put up to fundamentally show things were working. And then show the actual measurements that the USRP produced as the heart of the system. And I'll go through the signal processing we did, calibration, the image formation, and then some summary of some future work. So here are the goals. So the basic goal, the top level goal, is to demonstrate fundamental SAR type system performance with USRP as a back-end receiver exciter. And there was also several sub-objectives. And actually on the main project goal, one of the main ones was they're students, so they're in learning mode. And one of the main goals was to expose them to signal technology, signal concepts, and apply them with some real hardware to help build their skill set as they enter industry or grad school, wherever they're going. So that was really an emphasis too here. So we want to demonstrate some sub-objectives that involve some key radar techniques. We want to show how we can create virtual elements from an array. So to create 16 elements, you don't need 16 receive horns to do that. You can do that by creating things virtually. So we use MIMO techniques. We also have to coordinate a radar waveform with these switched elements. So there's some TDM involved. Now we have to upconvert to show that we can upconvert to X-band so we can get a smaller antenna. And then show that we can do digital beamforming because we get quality IQ in the spatial domain to form beams or angle of arrival for scattering in the scene. And then one big thing with a radar like this is you'll see in the ConOps it's a very close range scenario. You got to get rid of that transmit leakage. So we're running FMCW, so that transmit that comes over, you'll get that signal. It's as high as what you receive. So you got to be able to get rid of that. It's fundamental. And then the other thing was let's try to put as many of the signal processes functions in the GNU radio, in the graphical companion as we can, given time constraints in the semester. And we're only using cost components that you can get commercially. So here's a cartoon of the basic system concept. So what we have is 2 line arrays, okay? There's 8 elements that are receive, and there's 2 on the end that are transmit in this axis. And what they're going to do is we're going to digitally form beams. These yellow stripes are narrow pencil beams in azimuth that you form because we have a wide, very large lambda array in this direction. In the other direction, we just have a 1 dimension. So you get these striped 1-dimensional beams in space. Then we have another one in elevation, and that forms the same thing in the orthogonal axis. So if you get scattered energy at a certain range, you can form the union of that, and then you can kind of get a fix on where the scattered energy is going to be in the scene. The other dimension, so that's 2 dimensions in space. You got your as and your L. Now downrange, so there's a 3rd dimension. So at different ranges, you want to image what's at different ranges, so it's not ambiguous. So there we use an LFM chirp waveform, linear frequency modulated waveform, and we have enough bandwidth, and that was one of the critical driving things for the USRP is how much instantaneous bandwidth can we get out of that, because 50 megahertz of IBW is about 20, it's equivalent to like a 20 nanosecond pulse in the time domain. So that means you can, and with 1 foot per nanosecond, that means you can see things, you can discriminate things in range about 10 feet apart. So the more bandwidth you have, the more discrimination you can do in range. So really you have here is 3 dimensions available to do some imaging. Oops. The other point to make is there's no moving parts, so this is static. So we're going to form these beams by not moving a dish mechanically. We're going to form these digitally, all COTS, and we're going to be sending out a pulse. It's pretty long. It's 10 microseconds long. So, and with the range only 40 feet away, that's like a 10,000 foot pulse. So we're going to be transmitting and receiving at the same time. So we really have to separate those two returns. So one of the key concepts to understand is that when you do beamforming spatially in as and L, it's really dictated by how close you can get your elements. So in our case, we couldn't get the elements at lambda over 2. So the same way in the time domain, we have to sample things frequently enough so you don't get aliasing that corrupts your rendered signal in the digital domain. Well, in the spatial domain, when you sample a scene elementally, you have to have the elements close enough together, or you get grading lobes, which distorts your real space. So it's analogous to corruption. It's analogous to aliasing in the time domain. In the spatial domain, you get these what are known as grading lobes in your real space domain. So it limits how much you can then scan and digitally beamform. So these blue traces are basically this separation that I'll tell you why we have to go with that separation. You get grading lobes here, but at Borsite at 0 degrees, you're fine, but you get these grading lobes. And basically what happens is as D increases, D sine theta, okay, what happens at these other angles, you can actually have the signals all add in phase because they're so far apart, and it's modulo 2 pi with a wave in free space, that they add at other angles. So in this case, they added at minus 20 degrees, plus 20 degrees, and at 0 where we wanted it. So now when you do your scanning, when you scan this over to do your beamforming, to pull in energy at scatters at other angles, what happens, this moves this way too, and it gets into your field of view. So your unambiguous field of view is limited by the spacing between these elements. So we're forming 16 virtual elements we have a transmit here and 8 receive. So what we do is we transmit out T1, receive in RX1, and halfway in between is a virtual phase center. It's like having a transmit receive cell right at that position in space, but it's really from 2 apertures. So you go halfway in between, and from a phase standpoint, it's equivalent. So you go through and you out of transmit 1 and you go into transmit 2, 3, 4, all the way, and you create all these phase centers. Then you go into transmit 2, you measure all these, and you create these phase centers. So now you have 16, it's equivalent of like 16 separate TR cells, or TR elements. And what you're sacrificing is time. You have to do this, instead of getting them all at once and having 16, or 16 separate receivers with 16 separate antennas, and all that extra hardware. We're doing it with one transceiver, and then we have a switch network that switches the time multiplexes between them to save hardware. But you do sacrifice time. So that's the trade-off. So that's how we create our virtual elements. Here's the hardware. So here's the antenna array in elevation and azimuth. And each one of these horns, the aperture was pretty much dictated by the horn we could get that was cost effective. These horns are very expensive if you just go online and look for a metal horn that's plated. Well, we found a company that makes plastic horns that are plated for $20 each at X-Band. So we arranged those on this structure and separated them they're separated by 6 lambda, and the transmit and receive here are 3 lambda. So when you transmit out one and receive in all these others, you create these virtual phase centers out front for both axes. And then I'll get into this electronics module in a second. The electronics from past years is in this blue box. And so what we did this year, we said, okay, let's use the B200 USRP as the receiver exciter. So we're going to use a host, and we'll put in waveforms in here and transmit waveforms, get receive waveforms, and coordinate those waveforms between transmit-receive pairs. So here's a diagram of the entire system that we implemented. So there's an FPGA, I don't know if you've worked with Digilent eval boards, but we use the Nexus 3 eval board. It works at 100 megahertz, has a clock in it. We derived a 1 PPS to trigger the USRP to kick off the waveform. And then the FPGA also sends out discretes to control a single pole 4-throw switch for transmit and a single pole 16-throw switch for the receive. So we switch these things in concert to create these 16 phase centers. Since the USRP can't put out X-band, it puts out 2 gigahertz, and we upconvert that through 2 chains. We do the full thread with 2 chains. We upconvert to 10 gigahertz with a 7.8 gigahertz LO. And then on receive, we downconvert with that same LO. And so we're phase coherent all the way through, which is very important in a radar, because radar is basically a phase machine. You got to control the phase. That's what you're measuring. So here's a photo of the electronics box, the componentry inside. So all this is implemented inside there. So here's a detail of that electronics box. Here's a custom power supply that one of the students did. Here's the mixers, the up-down converter, basically mini circuits parts. Here's the FPGA eval board that was used to generate the 1 PPS and all the discretes to the single pole 16-throw switch. And there's a power amp and an LNA in here, etc. So there weren't really any size constraints. The main constraint or main goal was to use COTS parts that were readily available. So here's the flow graph that we use to do the full thread radar function. So the transmit part is up here. So we created a binary file in Matlab, and you can easily create it in octave too, and then send it into the USRP as the sync. So this is the transmit section. And of course, we want to look at it in the time domain. So we set up a measuring device to instrument to look at it here. We're running it at a 50 megahertz sample rate. We found that the highest we could run it at for a sample rate was 50 megahertz and get consistent performance. We tried, and we couldn't do you'll see, we couldn't do streaming. We'd had too many underruns and overruns. So what we ended up doing was we just sent out a coherent group of samples in packets. And then we were able to receive coherently without any dropouts. So we're at a 50 megahertz sample rate, which is about the max. And we were able, since we're IQ complex, we were able to get up to 44.8 megahertz of IBW, which is one of the most important parameters in the radar when you're trying to do ranging. So our RF was 2.2 coming out of here. And so going into the radio, we have 2.2 gigahertz, a carrier at 2.2 gigahertz with an LFM modulation on it. And then that comes into the USRP source here. And then we do the conjugate multiply with a version of the transmit. So this is the match filter. So if you take two LFMs, two chirps, and you multiply them together, and they come back at different times, you get an IF frequency. It basically compresses into a single frequency. So if something comes back at a further range and multiplies, you'll get a higher frequency down at IF, at baseband. So you can separate range in the frequency domain by how it multiplies out. So on receive, we take the receive signal, and then we do a conjugate multiply with a version of the transmit, and then we go into the instrumentation and take a look at it. And again, we couldn't get the streaming over the USB with 50 megahertz. So what we had to do, I think it's coming up next. Well, actually, it's going to be after this. This is the timing. This is what we had to do from a timing standpoint. So the transmit signal, so what we'd have to do is we transmit out of one, we receive out of one, and then what we want to do is have the LFM waveform synchronized in time right there. And then when we want to get the next virtual aperture where we transmit out of one and receive in two, then we want another waveform, and so on. So what we did is we created one waveform that had 16 pulses in it. So it had 8,192 complex samples that represent the whole coherent, what we call a coherent dwell. So everything that goes out here is phase controlled. And so you get this long pulse that goes out that has 16 segments in it. And each segment is going to be coordinated in time between a transmit and receive pair. And then we're going to receive those, digitize, and pull out the information we need to form a beam in as, L, and then downrange for the 3 dimensions. So here's an example of the instruments we used to evaluate what was going on. So up here, what you have is this is the demodulated transmit leakage. Okay, so this is clear scene and transmit leakage. So what we have here is there's nothing out in the scene, so we're looking at free space. But we get a huge transmit signal because when we transmit, it just jumps over to the receive, and that's what we measure. So you're going to receive that thing, and you can see it's pretty hardy. The signals that go out from the radio, the baseband modulation generator band that USRP, you can see these are the LFMs. There's 16 LFM pulses that go out. So there's one packet of samples that produces all this as a binary file that the USRP takes and spits out. And we coordinate the switching for each one of these pulses to coordinate with the right transmit-receive pair. If you look at the compressed output, after you multiply this with a conjugate version of the transmit, then you can see you start to get a lower frequency. There's a sine wave buried in here that corresponds to the range of the transmit, which is just really close. It just leaks right around. So you end up getting a low frequency. So now if you say, okay, that appears to be working, let's set up a scene where what we'll do is we'll have a corner reflector at bore site, and then we'll put one off an angle and see if we can discern those things spatially and also verify that they're at the correct range. So we're going to look at the 3 dimensions of fundamental capability here. So here's what we set up in a field at the school. Right, so we used a trihedral reflector because it has a real broadband response. You don't have to line it up perfectly with your transmit signal. You get a return from it without having it be perfectly aligned. So when we put that in the scene, here's the clear scene and a transmit leakage like I showed before. And then when we put in the corner reflectors, 2 corner reflectors and the transmit leakage, you see the transmit leakage now just over the 50 megahertz, this is before we compress it, has changed. That means we have returns that are coming back on top of each other. And then if you look after it's compressed, after you multiply it by a conjugate version, you can see that it's different. So there's something happening. We're we're getting the leakage, but we're also getting returns from those two corner reflectors coming back, which is what we want to see. So the next thing we did is, this is where we had to stop here in terms of the using the graphical companion. And we went into Matlab, but we could have easily gone into Octave. There was nothing too fancy here. So what the students then did is they took the 8,000 samples that the GRC produces as a binary file and put it into a complex domain into Matlab. The samples end up getting interleaved, so you have to move them around appropriately with a little bit of code. And then we got to reshape, since we're getting 16 pulses, we need to buffer them into 16 512 sample groups. And then when we FFT each pulse, we can see in range the leakage. We should be able to see in range the leakage and also the corner reflectors, and be able to discern them spatially when we do the rest of the processing. Where when we extract for each 16 pulses, when we get the range, what we'll be able to do is we'll be able to decompose angle of arrival in that spatial domain. And one very important thing is applying calibration to your bore site corner reflector that's right at 0 degrees. You have to calibrate that to get rid of all the phase errors in the hardware. And then we do an FFT in the spatial domain to get the final image formation. So here we are. This is 512 samples for one of the transmit-receive pairs. So I just picked one. I picked number 9. There's 16 of them. And I'm presenting here the FFT of 512 samples of the compressed received information through the radio. So these samples, this FFT was performed on samples received by the radio, full thread. And as you can see, it very nicely discerns the leakage and then the corner reflector that's 40 feet away. So if you have 10 feet of resolution, it turns out that, guess what? This is right about where it should be. So the corner reflector's here, the leakage is here. So now, very important, I can filter out this transmit leakage because it's at a separate frequency. So now what I do is for each one of those 16 pulses, I grab this bin here, I grab the peak, and I grab the I and Q phase. And now I form 16 I and Qs and then I'm going to Fourier transform in the spatial domain, and then it'll tell me the angle of arrival of the energy that came from each corner reflector. So I'm going to grab 16 IQs from this FFT bin, that cell right there. And before, one of the things you have to do before you do the final image formation is say, okay, if I just do a corner reflector, a single corner reflector at bore site that's 40 feet away, just one corner reflector, what I have to do is I measure the phase, the complex values, each one of the 16 values, and because there's going to be some variation just due to hardware changes, and what you'd expect is some symmetry across all the cells, because the path length difference from bore site to the ones on either side are about the same distance, so that corresponds to a phase that should be about the same. So you see that there's some symmetry. There's reasonable symmetry across that on how we have that lined up. So I neglected to mention that earlier. So this phase response for each element represents the measured phase of a corner reflector at bore site. And so what you need to do is you have to, since that's at bore site, you have to make those amplitudes all equal and have zero phase. So all you do is you take each one of these points, multiply it by the conjugate to get rid of the phase, and then divide it by itself to get equal amplitude. And then you take that conjugate multiply and you do that to all future data. And that gets rid of that corner, that calibrates you to bore site at 0 degrees. So when we put in the second corner reflector, after doing the calibrate to amplitude of 1 and 0 for this guy. When we put this corner reflector in there, what you end up seeing is the real and imaginary part. So this is the real and imaginary part for 16 of the 16 of the range of the 16 samples that were at the range of this corner reflector. And as you can see, they're starting to form a sine wave. And so what happens is as the scatterer moves further away in angle space, what will happen is that the frequency of this increases. So you use the Fourier transform to decompose this into a frequency, and the higher the frequency tells you where it is in the angle domain. So that's how you discern in the angle domain where one corner reflector is relative to the other to verify fundamental performance. So you're using the Fourier transform to decompose this into angle of arrival of the energy, because each scatterer at each angle is going to give you a different sinusoid response in the IQ domain, and the Fourier transform will decompose this into the different frequencies, which corresponds to different angles of arrival for the scattered energy in the scene. So this was the measurement. We were physically at 5.7 degrees, and when we did the beam formation, or the beam formation, we got another peak at around 5.7 degrees off here. So we're able to, in the angle domain, discern where these two corner reflectors are. Unfortunately, we ran out of time during the semester because these are undergraduate students. They were getting ready to graduate, so and the semester was ending, so there was really no follow-on. Could have done a lot more measurements. So I think this verifies fundamental performance, which was my main goal to achieve for this. So in summary, I would say that the USRP had sufficient phase stability over a coherent dwell of 10 microseconds worth of samples on a full thread, so we could do digital beamforming. It was phase stable enough. We couldn't do the streaming over 50 megahertz. With the USB 3, we had to send out this packet that had all 16 pulses in it. One thing we noticed is that USRP, the phase starts at a different value. Every time you send out a set of pulses and collect the data, it starts out with a different phase. But for beamforming, all you care about is the relative phase between the pulses. You don't really care about absolutely where they start. It's the phase change over the pulses that you're trying to get. So that didn't matter. You need sufficient IBW bandwidth to separate out the transmit leakage. So whatever leaks across, you have to get rid of that in the range domain so you can pick the samples off of at the range that you're interested in, that imaging. And then the other thing we discovered is that with the 1 PPS that launches the waveform out of the radio, well, okay, that's great, but there's a delay. When you say radio, okay, give me a waveform, there's a delay from when that waveform actually comes out the spigot of the radio. So there was an extra delay. We had to empirically determine what it was. And I think a better way to do that in the future is have the 1 PPS launch the waveform, but at the output of the radio, the transmit signal, couple off and detect a signal, have a detector that detects an edge, and then there's a discrete from the FPGA that says, okay, start the switching between the elements. That would be a better way to do it in the future. And for the future, another item for the future is we could collect data over different RF bands by moving the carrier around and stitch together the measured response with different carriers, because each different carriers would, of course, would increase our IBW and try to stitch those together. And then finally, we could add some of the process functions from Matlab or Octave right into the GRC modules, but we didn't have time. And that's all. Thank you.